Good day, everyone. This is Eldemar Miraflor with.
Charlene, Tabiosa, and
Arniel Arbole.
Today, we're going to perform the laboratory exercise number 2, which is the common emitter amplifier. So, the main objective of this laboratory exercise is to perform the operation of a common emitter amplifier. So, today, we're going to design a circuit form of our common emitter amplifier and then simulate it using a online circuit simulator called Falstad. So, without further ado, let's get started.
Basically, this is what a common emitter amplifier looks like. So, in our screen, we have schematic diagrams here. So, if we try to look at in the first diagram or figure, we have the base here, the collector, and the emitter and the lower part. Next, if we try to use or apply a BGT transistor, we have the second figure or diagram. So, as we try to look at it, we have base here, the collector, and the emitter and the lower part. So, again, there are two currents entering the transistor, which is the IB and the IC. And IE is the only current leaving the transistor. So if we try to get the total of the or the relationship of the current, so it is IE is equal to IB plus IC. So next, if we try to look at in the third figure or the lower part of our screen, so we have the circuit form of our common emitter amplifier. So we have the VCC here, the 5 resistors, which namely R1, R2, the resistance in the collector, next is the resistance in the emitter, and the reactive load or resistive load, So we have two capacitors here, and it is connected in a alternating voltage source. And again, our source or our circuit is connected to the ground. So basically, that is what our common emitter amplifier looks like. So we now know what it looks like. So let's go to the circuit simulator, and let's create and simulate our common emitter amplifier. So this is the circuit simulator that we will use, and it is called Falstad. So since the main objective of this laboratory exercise is to demonstrate the operation of a common emitter amplifier, so we have two ways in creating our circuit. So we can just hover our cursor here, then go to transistor and click common emitter amplifier. So as easy as that, we have a common emitter amplifier. However, if we want to know how each part of this circuit works and how to put them together, so we need to create it on our own, so to have a better understanding of it. So let's go to circuits, then blank circuit, and let's start drawing it. First, we're going to draw or add an input source, which is AC, which have a single terminal. So that. Then let's add a capacitor. So and next is let's add resistor. Here. I should stop that one. Okay. Next. Here. And after this, the resistor, we must add a transistor. Okay. The bipolar NPN type. So let's put it here. Then after that, another resistors. Next, let's create wire here. Then let's add another capacitor. So let's put it after the transistor here. Then another resistor or the resistive load here, and an analog output here, that one. So after that, let's put a voltage source or let's add a voltage source. Single terminal, that one. And lastly, we must add ground for here and here. So there you have it. We have a common emitter amplifier, and that is the circuit form. So we can tap run here, and this is what it looks like. So the currents are flowing. Okay. So from here on, Miss Tabiosa or Miss Charlene Tabiosa will set values in the parameters and input it, and she will explain the outcome of it.
Let's proceed on changing the parameters of our circuit. So the first thing that we will do is we manipulate first our resistors, the values of our resistors. Let's make this 110K. Then we will make this as 10K, our R2. And then for our resistive load, we will make this as 500K. And then our input is our AC signal and our VCC, and our output is our RC. So first we will manipulate in our AC, and we will check on how does it affect to our output. So from 50 hertz, our input is our current has the maximum of 1.136 MV in our output, and we will change this into 80. So let's check. So the current with 80 hertz, from 80 hertz, it changes the output into 1.142 MV. And we can see here also our parameters such as our current, our voltage, our frequency, our maximum in voltage, and our VRMS and our power. So our VRMS is 3.536, and the changes it occur on our output is that it increases. But let's change another value for our AC. Let's make this as 110. So let's edit this. So from 50, 80, now we have 110 hertz. Maximum current for our output is 1.154, and still it increases. Then for our VCC, we will make also changes in this, but we will make our AC first go back to its original value, which is 50 hertz. So this is the current for our 5 volts, and this is our input. So for our 5 volts, we have 1.161 volts, and these are the parameters as follows: our current, our voltage, and our power. Then we will change this into 10 volts. So as you can see, there are changes. It increases from 10. Our maximum current is now from 10 to 11, then 10.9 or approximately 11 millivolts. Then let's change this 10 volts into 20. So from 20 volts of VCC, our maximum current becomes negative 30.18 volts, our output. So it decreases. So let's go back to 10 volts again. It becomes negative 9.25 millivolts. And for our 5 volts, it becomes 845 microvolts. So in the in this in the input, there is a direct relationship between the changes in our AC. And for our VCC, there is still a direct relationship also for the effect in the output. And now let's change our output and let's check if there is a significant change to our input. So let's make this as 3K. So from our input, we have 1.717 millivolts, and let's make this into 10K so that we can compare it. So our volts becomes negative 96.786. And let's change this into 20. So it becomes 185 millivolts. So the relationship of the change in the output to the input is that as the resistance increases, our current decreases. So they have an indirect relationship. So now let's proceed on what are the interpretations on the waveforms on our circuit. So now I will give the floor to our third reporter.
Good day, guys. I'm going to present here our circuit presentation, which is the BJT BJT transistor. So I'm going to show to you what is the relationship of changing the frequencies from 50 to 110 and the voltages from 5 to 20 and the resistance of the collector of the transistor. How these values affect the waveforms from input to output. When you change these values, how does it affect the waveforms of the output? So first, I'm going to change the input signal into 50 hertz. So we can compare the output. First, here the waveform is like just regular sine, but the output here with a maximum voltage of 100 millivolts with the values of 5 volts. What will happen if I change the value of the input voltage to 10 volts? 10 volts, right?
Yes.
So as you can see, in the output section, the maximum voltage increases. So with that, there is a relationship between the input voltage from 5 volts to 10 volts, which is increases to 40, almost 5 volts. Now, what will happen if I change the RC value wait, to 5K? What will happen to the output voltage? Sorry. As you can see, there is no significant change in the values of the output voltage. So now let's change the frequency into much higher frequency into 80. So as you can see, there is a significant small change in the voltage output. But what if I change back to 5 volts with a frequency of 80 hertz? What will happen to the output voltage? So there's a significant drop in the voltage, even though we change the frequency from 50 to 80 hertz. So changing the frequency from 50 to 80 hertz, there is a small change in the voltage. What really is the the parameters that would change the output voltage is the input voltage. If there's a big, if you add uh, uh, a bigger value than 5 volts, so the output voltage will be also increase. So there's a relationship with that. So let's try to change this into 20 volts. What will happen to the output voltage? See, there's a sharp increase in the voltage from from millivolts to 14 volts. So in the relationship between the frequency to the input voltage is really not really evident in the output voltage, but the 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 bigger factor in determining the output voltage is the input voltage, which is the BECE that enters the transistor, determines the output of the the transistor. So as you can, let's compare the frequency input, the input frequency and the output frequency. Okay, let's. As you can see, the the sine wave here, that this one cycle from this point to this point, which is one cycle, the voltage here is almost 0 volts, compared to the output voltage, which is almost 190 degrees out of phase to the input voltage. This means that the transistor, the expected output of signal from angle zero here to the lagging of almost 90 degrees from the output. So this means that the transistor is working. Okay. To wrap up, guys, the relationship between the input frequency and the output voltage doesn't really affect, but what really affects the output voltage is the input voltage and the collector resistor has a significant effect on the output voltage for the transistor.
Okay.
So with our experiment already done, we have now a better understanding of how a common emitter amplifier works. So in the first part of our video, we know how to create a schematic diagram of our common emitter amplifier. Also, using a circuit simulator called Falstad, we were able to create or design our own circuit. Then we have a better understanding as well of how the parameters or the each part of the circuit works and how to put them together.
And also, we understand the relationship, our input and our output. And our input are our VCC and our AC signal. And it has a direct relationship to our output, which is our RC. So as the values of our VCC and our AC increases, the current also in our output increases. However, for our current in the output, as our resistance increases, our current decreases. And for our waveform,
Uh, the waveform is dependent on the input voltage in the VCC and the resistance on the collector. So the relationship between the two is that whenever the voltage increases in the VCC, the output voltage also increases. That is to certify that the BD transistor works as an amplifier, therefore increasing the signal voltage of the input to the output. The input signal is amplified by the BJT transistor, which is the output like this one. Whenever the VCC voltage is increased, the output voltage of the transistor also increases. That is the relationship between the two. It is directly proportional whenever the higher voltage, the higher the input. So input signals are is dependent on the supply voltage to the transistor, and therefore uh, the bigger the voltage supply, the bigger the output. That's all.
Okay, so that concludes our second laboratory exercise about the common emitter amplifier using BGT transistor. Again, this is Eldemar Miraflor with
Charlene Tabiosa.
And Arniel Arbole.
saying thank you.
God bless.
And bye.